Okay, welcome to another fabulous day in Calculus 3. We're going to do some more rectangular coordinates triple integrals, and then we're going to start something really exciting, triple integrals in cylindrical coordinates. Yeah, we're going to learn a completely new coordinate system for 3 dimensions. Yeah, very cool. But first, let's stay in the rectangular coordinate system. Okay, check out this triple integral. And the Q means the region of integration. And for triple integrals, the region of integration is a solid in 3D. So you'll see a Q here. Some books might show you a big E, or you might see an uppercase D. And it's all the same thing. They're meaning that the region is a solid. Okay, so the Q, the solid for us, is going to equal this set. This is set notation denoting the solid. So they're telling you all ordered triples, x, y, z, such that y lies between 0 and 1, x lies between y and 1, and z lies between 0 and xy. And that tells you how you're going to set up or iterate the triple integral. They gave you lots of information. Because the y had the pure numbers only, that tells you the outermost integral is going to be with respect to y. And then the inner integral, or the middle integral, is going to be with respect to x, because x is going from y to 1. And then z will be the inside integral. And they're telling you what the integrand is. So just copy it down. Now, what I like about this problem is not only do you have to be knowledgeable about set notation and using that information to help you put the limits on your integral symbols, this integration problem is going to involve IBP, integration by parts. And you guys are all graduates of calculus too, so you know how to do that. So it's going to happen. Do we do integration by parts at the very beginning? No, it's going to come somewhere in the middle of the problem, so be careful. First, let's do the innermost integral with respect to z, and that means that we hold x and y constant. And so we're going to use the exponential rule here with u substitution, and the exponential rule says the integral of e to the u du is e to the u, so you're going to need to identify for me the u and the du. So the u here is this little exponent, z divided by y. And when you take the derivative of z divided by y, with respect to z, you'll get 1 over y dz. Now, bad news, 1 over y is not contained in the integrand right now. And it is considered a constant, even though y is a variable. At this moment, since we're integrating with respect to z, y is considered a constant. So we need the 1 over y. So what we're going to do is we're going to put in a factor of 1 over y, provided we multiply the front of that integral by the reciprocal of 1 over y, which is y. So what does our integral look like at this moment? Well, I'm going to keep copying down the 2 outer integrals because we haven't done those yet. And then we're going to have this multiple of y sitting out in front of this integral e to the u du, where we have those choices of u and du already set up. And then this antiderivative is going to be e to the u, but then I'm going to back substitute for u because u is really, excuse me, z over y. Doing all my bean counting here and making sure everything's there. So I'm going to have my e to the z over y, and I'm going to evaluate that between the limits of 0 and xy. And I still have my dx and dy out here. Now, we're going to plug in the upper limit first, and you substitute it in place of the z because we just got done integrating with respect to z. And don't discount the 0, even though a lot of times when you substitute the limit of 0, everything goes to 0. This one is not. So watch out, because that's a common silly mistake that people make, especially on a quiz or a test, you know, because they're in a hurry. So you're going to have e to the xy over y minus e to the 0. Now, e to the 0 is just a nice number. It's just 1, of course. But you want to reduce this to lowest terms, this exponent, so the y's cancel. So all we have left there is going to be the e to the x. That's kind of where we're at right now. Okay. I'm going to distribute this y right now, and then I'm going to integrate with respect to x next. Okay. So that means I'm going to hold y constant. So right now we're down to a double integral, and you're familiar with dealing with double integrals because we spent the last couple weeks or so doing that. Oops, there still should be a dx here. So we're going to integrate with respect to x. So the antiderivative of y times e to the x with respect to x is just going to be y e to the x, since the antiderivative of e to the x is e to the x. And then the antiderivative of y with respect to x is y times x. Okay? And so now we're going to evaluate that between the limits of y to 1. Gotta be real careful here. Let's substitute the 1 first, and we substitute it in place of the x. Oops. Minus, and now we'll substitute the lower limit. And so what do we have now? Uh-oh. Yeah. So let's go ahead and distribute this negative and do a little bit of cleanup here, not much, but we have y(e), and that's e to the 1 is just e, minus y e to the y plus y squared. And we're going to integrate this with respect to y. And at this point, it's a calculus 2 problem. And this is going to require IBP. So let's just do this a little bit on the side. So let's just do a little scratch here. I call it scratch, but you know, this is something I would want to see on your quiz or exam. What is the integral of y times e to the y? So you're going to use IBP. So you're going to identify a u, a dv, the du, and the v, because this is going to be rewritten as u times v minus the integral of v du. That's the by parts formula. And if you remember from before, that anytime you have an exponential multiplied by a polynomial, the polynomial becomes the u. And the exponential e to the y dy will be the dv portion. Yeah? So du, which is the derivative of y, will be 1 dy, and v is easy because it's just e to the y. Okay, so now when we do this, we'll get y e to the y minus the integral of e to the y dy, but the integral of e to the y is easy, it's just e to the y. So that guy there, after we get done integrating, will be replaced by that difference. You have to be careful because there's a minus in front of that guy, so we will distribute the negative. See this minus right here? Oops. So what about these other terms? So when you integrate ye with respect to y, e is just a multiple, so you have e y squared over 2, and then minus the antiderivative of just the y there is y squared over 2. And now you've got this minus sitting in front of the y e to the y minus e to the y. And then you also have the antiderivative of y squared, which is y cubed over 3. And this mess here, you're going to evaluate between the limits of 0 and 1. And that's pretty easy. You're just going to put 1 in there. Be careful because the 0 might not do what you think it's doing. The first two terms will go to 0 when you substitute the 0, but and then this term will go to 0. But the e to the y is not. So you're going to have e to the 0. And I think that's the only thing that doesn't go away. Yeah. And so you've got this big mess here, and then you can clean this up. And I claim after the cleanup, just a little bit of arithmetic. These two terms in the middle cancel. Oh, that's nice. You're going to get a weird number, e minus 1 over 2 minus 2/3. That's the exact answer. Wow, crazy. And we're done. So what was the point of that problem? I love this problem because it's got a lot of different little subtleties in it. One is setting up the triple integral using the set notation, and then, gritting down and actually doing the triple integral from the inside out, and ending up with an IBP problem, integration by parts. Will you have any IBP on any quizzes or exams in this class? Yeah, of course. I love IBP. And you're all graduates of Calc 2, so you should be very comfortable doing some IBP stuff. Yeah, and that concludes that example. Let's do another triple integral. This time it's going to represent a volume. So recall that if you're going to use a triple integral representing volume, the integrand is a 1. This is when you're using a triple integral for volume. Now, double integral is different. Double integral, you're going to put the, typically the capping surface is your integrand, or if you're having a surface that's got a cap as well as an underbelly, then you're going to do capping minus the underbelly. So here, what do we got? We have x equals 4 minus y squared. That is not the capping surface. Be careful, because some students see that equation and they think that's it. And the hard part here is identifying what's what, because you have to set this up on your own. And that's why when a lot of students, when they're new and they don't practice, they see all this stuff, they start putting things in the wrong location. And I don't give you any partial credit for that. So be careful. So I claim z equals 0, which is the xy plane, is going to be where the base of the solid is. And z equals x is the capping surface. And that's just a plane. So it's just a flat capping surface. Now, what about this x equals 4 minus y squared? Well, that's a cylindrical surface, and that sort of gives the side of the solid. But what's going on in the xy plane? Let's figure that out. So we can take a look at the base of the solid. If you graph x equals 4 minus y squared, and I figured out what I was doing wrong with my graphing calculator the other day. I was using the minus sign instead of the negative when I needed a negative, and it didn't like that. It was being really grouchy. So what I want to do right now is show you how to graph this function of y, x equals 4 minus y squared, using parametric mode. So how would you do that? Since this is a function of y, when we parameterize it, you're going to let y equal t, and then x, which is 4 minus y squared, will be 4 minus t squared. And so make sure that you're in parametric mode. And I'll check my mode. Yep, I'm in parametric mode. Excellent. And then I'll go ahead and clear out this stuff that I was trying to work with last time. X is 4 minus t squared. And then my y is just t. Let me check my window. This window won't get the whole picture. Like, let me just show you. If I let t min be 0 and t max be 3, I'll only get a portion of the actual picture. So this one, I need my t minimum to be something negative. Oops, and I wanted negative 10. negative 10. And then my T max, let's have it be positive 10 so we can see. There we go. And there is a horizontal parabola opening up to the left. Oh, wonderful. Okay. The vertex is here at the 4. Okay, now what's the base of the solid? Does it go on forever and ever like this? It's like an infinity base? Nuh-uh-uh-uh-uh. How do you figure out where it ends? And this is where students have some problems. That's what I love about this problem, is it tests to see if you're thinking about the problem. This capping surface happens to cut into the XY plane, because if you do set Z equal to 0 in this capping surface, you'll get X equals 0. Oh, well, what's that? That's the trace that this solid makes as it cuts through the XY plane, and X equals 0 is a vertical line on top of the y-axis. So it turns out that the base of the solid is this right here. Got your horizontal parabola, but it's cut off. So no, it's not an infinity base. Be careful. So this volume triple integral, we can now go ahead and start trying to put the limits on there. Because this base is the type of region that lends itself better to horizontally simple, I'm going to use the dx dy order of integration instead of dy dx. You still could use dy dx, but it's a little bit yucky. So I'll show that to you after I get done doing it, what I claim is the easier way. So the easier way is to say volume is equal to dz dx dy. Z is going from a low of z equals 0 up to the capping surface, z equals x. Now, since we're choosing the horizontally simple choice, dx dy, for our order of integration, you need to put in a sideways little man here. And remember, when you do draw your little man sideways, his head has to be pointing to the right, feet to the left. So his head is on the parabola, so that has the equation x equals 4 minus y squared. His feet are on top of the y-axis, which has the equation x equals 0. And then what is y doing on this region? Well, you have to know what the y-intercepts of 4 minus y squared are. So what are the y-intercepts for x equals 4 minus y squared? Well, to find the y-intercepts, you know from your algebra and pre-calculus days, set x equal to 0, oops, and then solve for y. And you know, when you take the square root of both sides, you'll get 2 y-intercepts, plus or minus negative 2, or plus or minus 2 rather. So that will tell us what the limits are for y, negative 2 and positive 2. Yay! So if you get this far, I would definitely give you partial credit, because this is pretty hard to figure out the setup from scratch. So let's go ahead and do this integral quickly. The innermost integral is with respect to z, and there's nothing there, but it's understood there's a 1. So the antiderivative of 1 with respect to z is z. And then you evaluate that between 0 and x, and you'll just get x. And then that gives us a double integral. And folks, this double integral would be the way you would set up the volume if they had asked you for a double integral, because you would put the capping surface there in the integrand and so on. So once you set up a triple integral to represent volume, once you get to the double integral layer, that's what it would look like if they had asked you to set it up for the volume with a double integral. Cool. This is easy. Integrating x with respect to x, that's just x squared over 2. Going between the limits 0 to 4 minus, oops, that should be a y squared, my apologies, 4 minus y squared. And then When you plug in the 0, it's going to be 0, so I'm not going to bother here. But you'll have 4 minus y squared over 2. Oh, dear. FOIL, and I'm going to move the half out here. So I'm going to have to FOIL 4 minus y squared with itself. You know, first, outer, inner, last. And that's going to get me, what do we have here? 4 times 4, 16 minus 4y squared plus another minus 4y squared. I'll add those together. And then finally, negative y squared times negative y squared is a positive y to the 4th. And this is a super easy calculus 1 integral. You know how to do, right? It's a little bit messy because you have to substitute 2 and negative 2. So, you know, do all the arithmetic. And this is sometimes where students blow it. I know sometimes I blow this because I'll miss one negative and then boom, the whole thing goes down the tubes because of the one negative I forgot to put. You know how that gets. But after you do the arithmetic and you add and subtract like terms, you should get, and better get a positive answer because this is representing a volume. 256 15ths units cubed. Woo! And that is a positive value. Thank goodness. And that is volume using a triple integral. Yay. Pretty good, huh? I want you to notice that the base of the solid is not just relegated to the first quadrant. You got to be careful because sometimes they'll ask you to set up, you know, volumes where the base is only in the, you know, where the whole solid is in the first octave. So that means your base will be in the first quadrant, but don't assume it, because if you did assume it here, you get the answer wrong. A couple other things I want to say. This capping surface does happen to have symmetry while it's hovering over this base. So you could have used symmetry and then cut the base in half. But I want to warn you, if you do that in any problem, you have to, for me, prove to me that the capping surface does have symmetry with respect to the base. And if you can't, then I won't let you do it. Even if you get the answer right, I'm going to take off points. Because a lot of times the capping surface is all squiggly and curvy and whatever, and there may not be as symmetry as it hovers over the base, and you can't assume it. So if you can't prove it, I'm not buying it, even if your answer is right, and it just so happens that it is. In fact, I've done that as a true-false question in the past for Calculus 3, asking, oh, can I just cut this in half and say twice this is going to be the volume? For, you know, a capping surface that doesn't have any symmetry over the particular base. And a lot of students go, oh yeah, true, definitely, because look, the base of the solid has symmetry, so everything is symmetrical. Ooh, that's deadly to assume that. The other thing I want to say is, what if we had set this up the dy dx order? So I want to just show you what would happen if we did, because this is a really good teachable moment for integration. And, you know, you're all graduates of Calculus 2, so you should be able to handle what I'm about to show you. Yeah. Involves change of variables. So let's just do this problem again, where we have dz, dy, dx as our order of integration. So the limits on the z are still going to be the same. Like that's still going to go from 0 to x, okay? But now, since we're choosing the vertically simple order of integration, it's going to be different. The outer limits for x are 0 to 4, because x is going from pure numbers. But what is y doing? When you put a little man in here, and this is the vertical little man, the little man's head is touching the parabola, but so is the little man's feet. Uh-oh. What do you mean? Well, remember that parabola is given by x equals 4 minus y squared. Yeah. Well, you can't put 4 minus y squared here because that, first of all, that's going to violate one of the rules of iterating integrals where one of the variables of the limits matches the variable of integration. So that's not good. Well, what you're going to do is you're going to solve this equation for y. So I'll add y squared to both sides, and then I'll subtract x from both sides. Then I'll take the square root of both sides. Don't forget your plus or minus. And then I get two answers: positive square root of 4 minus x and negative square root of 4 minus x. The positive square root of 4 minus x is actually the graph of the upper part of that horizontal parabola. And so that is in fact going to be the upper limit for the middle integral. And the underbelly here of that horizontal parabola is the graph of, y equals square root of negative square root of 4 minus x. So that would be that. Now this doesn't look bad. It's like, well, isn't this just as good as the other way you set it up? Well, it should get you the same answer, 256/15, or at least it better. But the issue here is you are going to run into a little bit more difficulty integrating. It's not going to be as easy as the other one. The other one is just like, easy integration. Starting off, you're fine. You know, what's the antiderivative of 1 with respect to z? Well, we already know it's just z. So that's not going to be different. So what's the problem? I'm getting there. I'm going to show you in about 2 seconds. It's going to be kind of weird. Next, let's integrate with respect to y. Okay, x is held constant, so the antiderivative with respect to y is xy. Sure, nothing wrong there. This seems easy. Don't see the problem yet. We're getting there. Now, when I start substituting these limits, this minus I'm going to pull out, so I'll have a plus. Now let's add like terms. We have 1 apple plus 1 apple, and that's going to give us 2 apples. Now, you don't need trig sub for this integral. This is a change of variables integral. And when I teach calculus 2, and some of you in the room had me for calc 2, so this may look familiar, when you're doing change of variables, and this 2 is just bothering me, I'll pull it out. You use u sub, but you have to be really careful because it's not your usual u substitution. You let u be 4 minus x, but du is -1 dx, but you have an extra x here. So what the heck do you do? That's when you know you can't use regular power rule for the u substitution here. Here, what you're going to do is you're going to solve this for x. So I'm going to add x to both sides and subtract u. Then you get your dx, which is -1 du. And then you substitute all 3 of these back into the integral. So the integral becomes, when you're doing this change of variables technique, and I don't know if some of you maybe haven't seen this technique, but this is really important. And for those of you who are going to go on and take differential equations, for example, and you don't know how to do this, you're going to run into a problem. Somebody's going to find out you don't know how to do this. That's why I'm going over it for you. You're welcome. So I replace x with 4 minus u. This is going to become the square root of u, and then dx gets replaced with -1 du. Now this is still not integrable. I'm going to take this -1 and distribute it over the 4 minus u, so it becomes u minus 4. This guy I'm going to rewrite with exponents, since radicals are evil, and then I'll distribute the u to the half. And then I'll integrate using the power rule. Oh, man. And then I'll distribute this too. And then I'll also back substitute for u. What the heck was u? I forgot already. Ha, 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 ha. 4 minus x. And then you evaluate this between the limits of 0 and 4. Okay, I'm done. I'll let you do the rest, but hopefully you end up with the same answer as before. But this is known as the change of variables technique. Very wonderful and powerful integration technique. Typically, students see it in Calculus 1, but sometimes when I teach Calculus 2, I do a quick survey, and some people didn't get a chance to see it in their Calculus 1. So what was the point? Why did I even bother doing that? Like, why? You just wasted our time. No, I didn't waste your time. I wanted to show you that sometimes a region of integration, even though it is indeed both vertically and horizontally simple, sometimes there is an easier choice for integration. So in this case, my least favorite order, dx dy, was the preferred choice just for ease of integration. Okay, that was the point. And of course, my example 6, I wrote all over it. Let's do example 6. Example 6, I'm just going to set up, but do not evaluate a triple integral that would represent the volume of a solid in the first octant, bounded by a cylindrical surface, z equals 1 minus y squared, and lying between two vertical planes, given by the equations here, x plus y equals 1, and x plus y equals 3. So let's look at the capping surface first, shall we? Just for fun. It is a nice cylindrical surface, and it kind of looks like I don't know how you would describe it. Maybe so here we are in GeoGebra, and if I enter in z equals 1 minus y squared. That's our capping surface. So there it is. And it is hovering over a place in the xy plane. Since this is in the first octant, the base of the solid will be in the xy plane. And we could graph those. I don't know if this will graph. Let's see if GeoGebra does it. Y1. Yeah. So that's a vertical plane. That's giving sort of one of the sides of the solid. And then the another side of the solid is x plus y equals 3. And this is really hard to tell. Like, what the heck? The solid is found in between those two green planes. So it's really hard to visualize here. But let's try and get back to here. So I'll try to help you visualize it. So the base of the solid, let's do that first. If you graph x plus y equals 1, which is, I'm going to make it easier. Let's graph y equals 1 minus x. And I'm only graphing the part there in the first quadrant. And then y equals 3 minus x. Okay. So this is the base of the solid. Ooh. Oh, no, wait. Sorry, I got one more thing. Not yet. What about when z equals 0? Because this cylindrical surface actually chops into the xy plane. So we want to see the trace. And the trace is going to be given by 0 equals 1 minus y squared. Solving for y, we get that y is equal to plus or minus 1. And we don't care about the negative 1 since we are only looking at the first quadrant. Y equals 1, though, is this horizontal line. So the base of the solid is this little sliver here that I've shaded in. Now, folks, if you did try to set this volume up using dy dx, you'd have to chop up this region into 4 pieces because there's actually 3 pieces because there's 3 different upper and lower limits. So that's a poor choice. The better choice would be to pick dz, dx, dy, because this region is much better. You only need one single integral, not three separate triple integrals to do it. So z is going to go from the xy plane, which has the equation z equals 0, up to the upper limit, which is z equals 1 minus y squared, and then dx dy, put in your vertical or your horizontal little man. Okay, and the upper limit is going to be this equation here, and if you solve this equation for x, you get x equals 3 minus y, so that's the upper limit for x. And then his feet are on this other diagonal line, which has that when you solve this equation for x, you get x equals 1 minus y. And y is going between 0 and 1 for the outermost integral. Always has to be pure numbers. I'm not going to evaluate this because they didn't ask me to. They said set up and not evaluate it. Okay, I won't. So what would the solid look like? So the solid, this is a little bit tricky, but the z equals 1 minus y squared, when you graph just the portion of it here, it looks like sort of this curvy thing here. I'm just looking in the first octant, and it's hovering over this base. I'm going to try to draw that base in 3D. Boy, is that not easy. This is the y, this is the x. The base is that sort of little sliver right there. So if you can imagine a solid that's got this curvy thing as the capping surface, and then down below here, that little sliver that looks like this as the base, that's the volume that you're trying to find. That's solid. Pretty weird, huh? And that's the end of that example. Example 7, set up, but again, do not evaluate a triple integral representing the mass. So here's a mass problem. Oh my God, the mass of a solid. I haven't shown you how to do that yet. Well, I alluded to it last time. So the mass of a solid needs a triple integral where you put the density function for your integrand and you integrate over the solid that you're trying to find the mass of. That's how you use a triple integral to find the mass of a solid. Okay? So we're going to just set this up. And they did give us a density function, so we're good to go. Just so you know that there is life after Calculus 3, here is a PDF that a former student of mine who is currently finishing up his, I think, biochemistry degree at State, and he wants to go to grad school too. He had me for Calc 2 and Calc 3. Great student. I ran into him. Check out this. This is a physical chemistry book, the thermodynamics, I think, text. So here they're doing a triple integral right there, okay? And not only is it a triple integral, oh my goodness, it's an improper triple integral, because look at the limits on this triple integral. Aha, we have infinity there. So this is improper triple integral. I love this. Isn't this great? So for those of you who think, well, I'm never going to see these triple integrals again after I get done with this class. Well, when you get, if you're mechanical engineering and you take thermodynamics, you will run into it again, and you'll be so glad that you know what you're doing, right? And I don't want to scare anybody, but if you keep looking through this book, what do you see there? That is I think that you would call that a sextuple integral instead of a triple. You've got 6 integral symbols all there. Oh my goodness. And then I think you're figuring out the energy of the particle or something. You've got positions of the particle. So you've got 6 different integrals to go evaluate if you were taking this class. Pretty amazing, huh? Of course, you'd start from the innermost one first, and then you'd work your way out. Right now, everybody in the room should be saying, wow.
I'm scared.
Don't be scared. Well, it could be really fun for you, fun and exciting. Okay. We won't be doing that in this class. I'm just bringing it into the conversation to point out to you that this stuff is relevant for your future. You know, being good at mathematics, you're going to run into more mathematics. So we're just preparing you here. Okay. So let's do the mass here. So how do we do that? We have an upper hemisphere, and if you graph that upper hemisphere, it's a sphere centered at the origin of radius 1, but you're only looking at the upper hemisphere. Okay, so that's what that graph would look like. And you're trying to find the mass of it. So how would you do that in rectangular coordinates? Because this doesn't look like it would be very fun in rectangular coordinates, and it's not going to be. It's going to be kind of gross. But that's the segue into the next section. So the mass would equal triple, triple, triple. I'm going to put my density function as the integrand, and then let's do dz, dy, dx. Now the z limits are z equals 0, because the base of the solid is in the xy plane. And the capping surface was the upper hemisphere, z equals square root of 1 minus x squared minus y squared. And in this capping surface, since it does cut into the xy plane, you set z equal to 0 to see the trace in the xy plane. And what happens when you set z equal to 0 in this equation? Well, square both sides to get rid of the radical, and then add x squared and y squared to both sides. And I get a circle centered at the origin of radius 1. And that, in fact, is what the base of your solid is doing. I hope that makes sense, because if you look here at this picture I have, you know, here in the xy plane, you've got a unit circle. And so if you're going to iterate this triple integral, x is going from -1 to 1, and then y is going from negative square root of 1 minus x squared to positive square root of 1 minus x squared. And this would probably be a horrible triple integral if you had to integrate it using rectangular coordinates. You would definitely want to try and change the coordinate system, and that's what you would do. So we are officially done with triple integrals in rectangular coordinates. Congratulations.